You felt it before. You take two magnets, push them together, and suddenly, there's a wall. An invisible, spongy cushion that refuses to let you pass. It feels so physical, almost like squeezing a rubber ball. You think you understand it. It's just magnetism, right? Simple. Wrong. What you're feeling in your hand isn't simple. It is a force so fundamental, so incredibly strange, that when Richard Feynman, a Nobel Prize-winning genius, was asked why it happens, he didn't just hesitate. He refused to answer. The interviewer asks a perfectly reasonable question. What is this feeling between the two magnets? Why do they repel? You expect a textbook answer. You expect him to say magnetic fields or poles, but Feynman doesn't do that. He sits back. He looks almost frustrated, and then he starts talking about his Aunt Minnie in the hospital. He talks about slipping on ice. He talks about aliens coming to Earth. If you watch the clip, it feels uncomfortable. To many people, he looks arrogant. The comments section is full of people saying, "Just answer the question," or "Why is he making the interviewer feel stupid?" It looks like he's dodging the question because he thinks the guy isn't smart enough to understand the answer. But that is not what is happening. Feynman isn't being difficult. He is being rigorously, painfully honest. And he refuses to give a fast food answer. He knows that if he just gave a fancy scientific name, he wouldn't be explaining anything. He would just be swapping one mystery for another label. He realizes a problem that most of us ignore. To answer why something happens, we have to agree on a framework of what is true. We have to agree on what we allow to be the final answer. If you don't accept the fundamental laws of physics as the bottom layer of reality, then every answer he gives will just lead to another why, and another, and another. He isn't trying to gatekeep knowledge. He is trying to show us that the question itself is a trap. Take the example of your Aunt Minnie in the hospital. Why is she there? Because she slipped on the ice and broke her hip? That answers the question. People are satisfied. But if you are like Feynman or a curious child, you ask again, why did she slip? Because ice is slippery. Everyone knows that. But why is ice slippery? Now the problem gets interesting. You might say, well, when you stand on ice, the pressure of your weight squeezes it. And because water is strange, when you squeeze ice, it melts just a tiny bit. You create a momentary microscopic layer of water under your shoe. You aren't actually slipping on the ice. You're slipping on that instant water. But why? Why does pressure make ice melt? If you squeeze almost anything else in the world, it gets solid, not liquid. It happens because water expands when it freezes, and the molecules arrange themselves in a very specific open, airy structure to become ice. They need space. So when you step on it, when you apply pressure, you are physically crushing that structure. You are forcing the atoms to collapse out of that open crystal arrangement, and they snap back into the tighter, jiggling chaos of liquid water. So, look at where we are. We started with a broken hip in a hospital. We asked why just a few times, and suddenly, we aren't talking about Aunt Minnie anymore. We are talking about the expansion of matter, the structure of crystals, and the molecular bonds of hydrogen. We traveled from a family accident to the fundamental laws of chemistry in 3 moves. This is the danger and the beauty of asking why. If you keep going, you eventually leave the familiar world behind and end up deep in the realm of invisible forces. So, let's try to cheat. Let's try to give you an answer that feels satisfying without going into the deep physics. You might say, okay, I get it. The magnets attract because it's like there is a rubber band connecting them. That feels right, doesn't it? You know what a rubber band is. You pull it, it pulls back. Case closed. But if we are being honest, if we are really asking why, we have to ask, why does a rubber band pull back? Is there a ghost inside pulling the ends together? No, it's the jiggling. Inside that rubber, There are long, tangled chains of molecules. When the band is loose, they are curled up in a messy, comfortable knot. But they are not sitting still. They are vibrating. They are shaking. They are jiggling due to thermal energy. When you stretch the band, you force those chains to straighten out. But they don't want to be straight. They are pounding against each other, wiggling, trying to snap back into that messy, curled up shape. That wiggling is the force you feel pulling your hand back. But wait, if you pull too hard, why doesn't the band just snap apart? What holds those chains of molecules together? It is the electrical force. It is the attraction between the atoms holding the rubber together. So, look at what you have done. You tried to explain the mysterious force of magnetism by comparing it to a rubber band, but the rubber band only works because of electrical force. You are using the electromagnetic force to explain the electromagnetic force. You haven't explained anything at all. You have just walked in a circle. You cheated. Let's get real for a second. Look at where you're sitting right now. Maybe you are on a chair, maybe on a sofa. You feel it supporting you, right? It feels solid. It feels like you are touching it. But you are not. If you could look at your own body with a microscope powerful enough to see atoms, you would see something incredible. The atoms in your body and the atoms in the chair are not touching. They are hovering. There is a tiny, invisible gap between you and that seat. Why? Because surrounding every single atom is a cloud of electrons. And electrons carry a negative charge. And what happens when you try to push two negative charges together? They hate each other. They repel. They scream, "Get away!" When you sit down, the electrons in the seat of your pants are pushing against the electrons in the fabric of the chair. And that force, that electrical repulsion, is so incredibly strong that it holds your entire body weight up against the pull of gravity. You're literally floating on a cushion of electrical force fields. And here is the kicker. That force pushing you up, it is the same force that pushes your hand away when you hold two magnets together. It is the exact same beast. The only difference is, in the chair, the force is happening at a microscopic distance, so you perceive it as solidness. In the magnet, we have just tricked the atoms into lining up so that this force reaches out across a distance you can see. Think about what that means. This force isn't just a party trick for holding photos on a fridge. It is the reason reality exists. Without this electrical repulsion, matter would pass right through matter. You would slip through the chair and through the floor and fall straight through the earth to the center of the universe. The only reason the world is solid, the only reason you can stand, sit, or hold a cup of coffee is because of this invisible force. So here is the mechanism you wanted to know. Here is the how. If electrical force is everywhere, why doesn't a piece of wood stick to the fridge? Why doesn't plastic repel plastic? The answer is inside the atom. Every electron in the universe is spinning, and because it is a charged particle spinning, it acts like a tiny, microscopic magnet. This means that right now, inside a block of wood, there are billions of magnets. Inside a plastic cup, there are billions of magnets. But they are a mess. In a piece of wood, the electrons are spinning in every possible direction. One spins left, the neighbor spins right. One points up, the other points down. They are fighting each other. It is total chaos. The magnetic field of one electron is perfectly canceled out by the magnetic field of its neighbor. And it is like a stadium full of people where everyone is shouting a different word at the same time. The result is just noise. Zero net force. But iron is different. Iron is special. Due to the specific crystal structure of iron, the electrons are not independent. They are social. They like to copy their neighbors. If you can get a few of them to look in one direction, the others say, "Okay, I will look that way too." They stop jiggling randomly. They snap into alignment. They line up. Suddenly, you don't have a mob. You have an army. Billions upon billions of tiny electron magnets are now spinning in perfect unison. They are all pulling in the exact same direction. And this is the magic. The force doesn't just add up, it amplifies. It compounds into something massive. Yet that pull you feel in your hand is the collective power of Avogadro's number of atoms all working together. It is the only time the quantum world gets big enough for you to play with it. So, we return to Feynman's frustration. He wasn't trying to be difficult. He was trying to tell us that we had hit the floor. We had hit rock bottom. In science, we explain complex things by breaking them down into simpler things. Why does the car move? Because of the engine. Why does the engine work? Because of gas exploding. Why does gas explode? Because of chemical bonds breaking. Why do bonds break? Because of the electromagnetic force. But here is the problem. When you ask, why does the electromagnetic force exist? There is nowhere left to go. There is nothing simpler than this force to explain it with. You can't describe the foundation of the house using the roof tiles. You can't describe the alphabet using the words cat or dog. The alphabet is what makes the words possible. Yet this is what Feynman meant when he said he couldn't explain it in terms you are familiar with. He wasn't being arrogant. He wasn't hiding a secret. He was admitting the ultimate humility of science. He was telling us that at some point, you have to stop asking why and start accepting is. Magnetism is fundamental. It is one of the base layers of reality. It doesn't look like a rubber band. It doesn't look like a spring. It doesn't look like anything else in your life because everything else in your life is made out of it. It is the rule that makes the game possible. You have to accept it as a given. It just is. Remember Aunt Minnie? We left her in the hospital because she slipped on the ice. I told you earlier that she slipped because pressure melts the ice into a thin layer of water. That is the story you will find in almost every old textbook. It is the story that satisfies your curiosity so you can stop asking why. But I have a confession to make. That explanation is wrong. If you actually do the math, it falls apart. A person simply isn't heavy enough. The pressure of your shoe is not enough to melt ice that is 20 degrees below zero. Yet, you can still skate on it. You can still slip. So, if pressure isn't the answer, what is? We are back to the jiggling. Deep inside a block of ice, every water molecule is holding hands tightly with its neighbors in a perfect, rigid crystal grid. They are locked in place. But look at the surface, and look at the very top layer of atoms. They have neighbors below them, but they have no neighbors above them. They are exposed. They have no one to hold on to. Because they are untethered, these surface molecules are restless. They are vibrating. They are wiggling. Even at freezing temperatures, this top layer acts like a liquid. It is a permanent, slippery skin of molecular chaos. Feynman brought up the ice for a reason. He wasn't dodging the question about magnets. He was showing you that even the most boring, everyday thing, a patch of ice on your driveway, is actually a deep mystery involving molecular surface dynamics that scientists are still arguing about today. If we can't give a simple answer for why you fall down in the winter, how could we possibly give a simple answer for the invisible force that holds the universe together? So, we have traveled a long way from a simple question about magnets. We went from Aunt Minnie in the hospital, to the slippery surface of ice, to the electrons in your chair, and finally, to the fundamental laws of nature. This is the world Feynman saw. It isn't a quiet, static place. It is a vibrating, jiggling dance of energy. It is a universe held together by invisible rules that we can describe but never fully explain, and that is okay. There is a beauty in not knowing the ultimate why. There is a joy in just accepting that the universe plays by these strange, magnificent rules. So, the next time you hold two magnets and feel that invisible wall pushing back against your fingers, don't just see two pieces of metal. Look deeper. Realize that you are holding the fundamental fabric of reality in your hands. Yet you are feeling the very force that prevents the entire universe from collapsing into itself. That is the secret. That is what makes it fun to imagine.